Hi guys, I am Sicheng, and today I'll be doing a video on PNC, which is, I suppose, is a topic that a lot of you struggle with. Let's start. Let's start by explaining the multiplication principle. So suppose you have let's say you are choosing, you have to go out and you're choosing what to wear. You can choose between 3 shirts and 4 pairs of pants. So how many ways are there to choose a combination of shirts and pants to go out? The answer is 3 times 4, which is also 12. This should be quite simple, right? So let's say the shirts are S1, S2, and S3, and the pants are P1, P2, P3, P4. So let's say you have chosen shirt SI. Then afterwards, no matter what shirt you choose for SI, there are always 4 choices for your pants: P1, P2, P3, P4. So for each shirt, S1, S2, S3, they give you 4 options for pants. So 4 options for each of the shirts. And since there are 3 shirts, you have 3 times 4, which is 12 ways to choose your shirts and pants. Simple enough, right? So now let's say you have to choose a pair of socks as well. Let's say you have 5 pairs of socks, and they are numbered K1, labeled K1, K2, K3, K4, K5. So now what are the number of ways to choose shirts, pants, and socks? So let's say you have chosen your shirts and your pants already. Then this is your combination, SIPJ. Then afterwards, how many choices are there to choose your socks? There are 5 ways, right? You can choose, no matter what shirt or what pair of pants you choose, there are always 5 ways for you to choose the socks, because you can choose K1, K2, K3, K4, or K5 in any way you like. And since here there are already 3 times 4 ways to choose your shirts and your pants, there are 5 options for you to choose your socks afterwards. Then there are 3 times 4 times 5 equals 60 ways to choose your shirts, pants, and socks. Simple, right? So in general, let's say if you have how to say if you have, let's say, a sequence of independent events, E1 followed by E2 followed by E3 followed by E4, and so on, and these are independent. E1 has M choices, E2 has N choices, E3 has P choices, E3 has Q choices. Then the number of ways to choose for all of them to occur in sequence is MNPQ. Or let's say there are N events. En. Then number of ways is A1, A2, all the way to AN. Then the number of ways for these events to occur in sequence, like choosing shirts or socks or whatever, is A1, A2, all the way to AN, the product. Yeah, so this is the multiplication principle, which I think you all should understand already. Now, suppose I ask you this question. How many ways are there to arrange the digits 1, 2, 3, and 4 to form a 4-digit number? So it can be 1, 2, 3, 4, or 4, 1, 2, 3, or 2, 4, 3, 1, or something like that. So how many ways are there to do that? So let's try listing out. Okay, 1 2 3 4 1 2 4 3 1 3 2 4 1 3 4 2. Okay, I think you can just wait. Yeah, so I've listed everything out, and if you count, there are 24 ways to form such a 4-digit number. So so this is basically called brute forcing, or just listing. If worst comes to worst, you are stuck on a PNC question and you have a lot of time left, it's okay for you. If you want, it's okay for you to just start listing if the PNC question isn't that long. Yeah, but anyway, what can we glean from all this listing? So as you can see, there are 6 numbers starting. So there are 6 numbers starting with 1, 6 numbers starting with 2, 6 numbers starting with 3, and 6 numbers starting with 4. Yeah, so let's focus on the numbers with the number 1 first. So starting with 1, you have, so let's say starting with 1, the remaining numbers, you can start with either 2 or 3 or 4. Then afterwards, then let's say you start with 2, then afterwards you start with either 3 or start with either 4. Then then the remaining is quite obvious. So I think, mainly I think the process for choosing is something like this. So let's say you choose the first number, the first digit, which I'll just call A1. Then how many choices are there for this? It's 3 choices, right? Yes, there are 3 choices. And the main thing to note is that these 3 choices could be different depending on what A1 is. If A1 is 1, then the 3 choices are 2, 3, 4. If A1 is 3, these 3 choices could be 1, 2, 4. But the main thing to note is that there are 3 choices. So there are 3 choices for this. So let's say you choose A2. Oh yeah, there are 4 choices for A1, right? Yeah, so there are 4 choices, then 3 choices for A2. Then afterwards, there are 2 choices for this digit. And by similar reasoning to what I explained just now, no matter what are your choices, what you chose for A1 and A2, there are always 2 choices for this, right? Yeah, so let's say you chose A3, then in the end there's only 1 remaining choice for the last digit, which you just call A4. So because of this, so as you can see, there are 4 choices for A1, the first digit, 2 choices for A2, 2 choices for A3, 1 choice for A4. So the number of ways is 4 times 3 times 2 times 1, which is 24. Then I think by now you should know you can expand this line of reasoning to n digits. So let's say this is an n digit number. The first digit A1, there are n choices. Then the second digit is you have n minus 1 numbers remaining, so you have n minus 1 choices. So choose A2. Then here there will be n minus 2 choices. Choose A3, and so on until you get 1. Then the number of ways for choosing such an n digit number would be n times n minus 1 times n minus 2 times all the way to 1. And this is known as n factorial. Okay. Yeah. Okay, yeah. Okay, so now let me modify the question. Let's say you are choosing a 4-digit number. You want to form a 4-digit number from 1, 2, 3, and 4. But the restriction is that 4 cannot be in the first place, in the first digit. So what do? So you follow this way of counting. So here you have, let's follow this line of reasoning again. So in the first digit, you have, instead of having 4 choices, you have 3 choices now, because you have, you can only choose 1, 2, or 3 for the first digit. Then for the second digit, do you still have 3 choices? Or yeah, you have, basically you have 3 choices. If you choose 3 for this, it's 1, 2, 4. Now 4 can be used as a second digit. And if you choose 1 here, then this will be 2, 3, or 4. Then you use the same line of reasoning. Eventually what you get is 3 times 3 times 2 times 1, which is 18. Then let's check back here to see if it's correct. So if 4 cannot be the first digit, that means these numbers are all gone, right? Then if you count all the remaining numbers, there should be 18 of them. Okay, yeah. So now let's suppose that, let's change the restriction a little. What if 4, instead of the restriction being 4 not, instead of 4 not being allowed to be a first digit, why not let's have 4 not being allowed to be the last digit? So if you do this way of counting, you realize you can try. Let's say, so here there will be, so it can be like, here there will be 4 choices, then here there will be 3 choices, here will be 2 choices, but then you think, oh wait, what if I'm left with 4 over here? The main thing is to note is that you don't have to go from the first digit to the second digit to the third digit to the last digit. You can also go from, let's say the last digit first, followed by the first digit, or then the second digit or third digit, or basically you can choose them in any order you like. So any order you like. So but you can, like, so here's the 4-digit number. Let's say you choose your number. So since 4 cannot be the last digit, we choose the last digit first. So this can be, let's the last digit be A1, then it could be 1, 2, or 3. So there are 3 choices. Then afterwards you just choose the remaining 3 digits in whatever order you wish. So let's say this is the second one. There are 3 choices, right? Yeah, so if let's say you choose 2 here, then here will be 1, 3, or 4. Then afterwards 2 choice, let's say you choose this as choose the first digit next, then there will be 2 choices, then the remaining one will go here. Okay, so it's still, the number of ways is still 3 times 3 times 2 times 1, which is 18. Then if you count, you cancel out this number, this number, this number, this number, this number, and this number, you'll see that there are indeed 18 numbers that don't end in 4. Okay, yeah. So in general, I think the main thing to note is that to settle the restrictions first. So the restriction I set over here is 4 cannot be the last digit. So what you do is you choose the last digit first. If let's say the restriction is 4 cannot be the second digit, then you just choose the second digit first, then the remaining, then afterwards you can just choose the remaining 3 digits like you would normally do. Normally choose a 3-digit number. Okay. Yeah. So let's change the restriction a little. Now let's say the restriction is that 1 must come right before 2, or 2 must come right after 1. So you can have 1, 2, 3, 4, but you cannot have 1, 3, 2, 4, something like that. So how many ways are there to choose such a number? So some of you are probably thinking, oh, I choose my so as you can realize, this sort of way of counting will will either lead you nowhere or will be quite messy. You can try to do it, but I'll not go. But I think I'll not go that way. I think the way to see it is not like, oh, there are 4 digits and I must choose each 4 digit singly. Instead, I can choose. So you're probably thinking, these 4 numbers, I need to slot them into 4 slots, right? But for this case, I think what is better to see is you have 3 slots and 3 things to slot into the slots, and the 1, 2 come together as one big block together. So number of ways to do this is you can have, let's say, 1, 2, 4, and 3, or you can have 4, 1, 2, or 3. Then in the end, even though you have 3 slots, you'll end up with a 4-digit number, right? So since there are 3 factorial ways to do this, like by the reasoning just now, so there are 3 factorial ways, which is 6 ways to choose such a number. Yeah. Then what if, let's say, the 1 and 2 just need, let's change the restriction a little. The 1 and 2 just need to be together, but they don't necessarily need to be in this order. So that means you can also have 2, 1. Then for this, what you do is you consider the 1, 2 as one block, but you put them as one block first. You notice, right? After you settle the 1, 2 together, there are 2. You can have either 1, 2, or 2. You can either keep them as is or switch them around to form 2, 1. So to keep them as one block first and slot them in, and then within the 1, 2, you choose either to keep it as 1, 2, or you switch them around, or you choose either 1, 2 or 2, 1. So since there are 2 ways to do this, like after you slot all the 3 and 4 and whatever, then you choose what goes in this 1, 2 block thing here. So there are 2 ways to do this. So there are 2 times 3 factorial, which is 12 ways. Yeah. I think the main thing to note here is to be flexible in your thinking about the slots. So in let's say there are 10 seats. Let's say the question tells you there are 10 seats and there are 10 people going to sit in these seats. Then the question also tells you 4 of the people need to sit together. So even though the question gives you 10 seats and 10 people, you don't go and try and slot the 10 seats into the 10 people into the 10 seats and then try and figure out from there afterwards. It's going to be quite mafan. Like I said, you need to settle the restrictions first. So you need to treat the 4 people who are sitting together. You need to treat the 4 people sitting together as one block. One block, you slot it into, like, let's say, yeah, then you just put it wherever you need. Then you put the rest of the other 6 people afterwards. Then afterwards, within the 4 people, if the question didn't specify any other restrictions, then you figure out how to arrange the 4 people within this block afterwards. Yeah. So main thing to learn is try and settle the restrictions first. Don't settle it afterwards. Yeah. Now let's say you have 5 numbers, 1, 2, 3, 4, 5, and you want to choose 3 of them to form a 3-digit number. How many ways are there to do this? I think for this, all you need to do is just apply the multiplication principle. Like let's say for this number, how many? Oh yeah, there's no replacement, so you cannot have, like, let's say 1, 1, 2. So all you need to do is apply the multiplication principle. Here for first digit, how many choices are there? Then after you finish choosing the first digit, how many choices are there for the second digit? Then after that, how many choices are there for the first digit? So as you can see, there are 5 choices for first digit, followed by 4. Then let's say 5. Whatever number gets used up, that leaves you with 4 numbers for the second digit. Then that leaves you with 3 numbers for the second digit. So the number of ways is 5 times 4 times 3, which is 60. Then now let's say there's replacement. So for example, there's replacement, so you can choose like 5, 5, 5. So there'll still be 5 choices for the first digit, but then for the second digit, it doesn't matter what you choose for the first digit, right? So there'll be 5 choices, and for the last digit there are still 5 choices. So afterwards, so for this there will be 5 cube choices, which is 1 to 5 choices, 1 to 5 ways to arrange this 3-digit number. Yeah, so this is basically the 1.5 in the tutorial, which is also just a simple application of the multiplication principle. Now in general, right, for let's say n objects, you want to choose R to form like, let's say a line or and you want to arrange R objects from these n objects. Then it's basically just, for first one there are n choices, second one there are n minus 1, so on until the last one there are n minus R plus 1. So just multiply all these together to get the number of ways. Yeah. That is if there's no replacement. Then if there's replacement, then it will just be n times n times n all the way to n equals n to the power of r. Okay. Yeah. Oh yeah, and this is equal to n factorial over n minus r factorial, because if we multiply this thing by n minus r factorial, we get n factorial. So now let's say you want to arrange 4 digits to form a 4-digit number, but the numbers are 1, 1, 2, and 3. So basically your 1 gets repeated in the form of a 4-digit number. So how do you do this? So let's say you treat your ones as 2 distinct numbers first. Then afterwards, let's see what as you know from just now, there are 24 ways to arrange such a number, right, with 2 distinct ones. So let me list them out. So these are the 24 ways to form a 1A 1B 2 3 4-digit number. So as you can see, there are clearly some duplicates. For example, 1A 1B 2 3 and 1P 1A 2 3. So what we do is what if we cancel out duplicates and form a new number and write out the new numbers over here. So let's say 1A 1B 2 3 1B 1A 2 3, you get 1 1 2 3. 1A 1B 3 2 and 1B 1A 3 2, you get 1 1 3 2. 1A 1B 2 3, 1A 2 1 3, 1B 3, 1B 2 1A 3, you get 1 2 1 3. 1A 1A 3 1A 3 1B 2 and 1B 3 1A 2, you get 1 3 1 2. 1A
So
1A 3,
now let's say
1B, you cancel these two, you get 1 3 2 1.
5 numbers 1 2 3 4 5.
Yeah, and if you
You
cancel
want-
these two,
You want to
you get 1 2 3
select
1. 3 numbers.
So basically what you notice that
But
is that
to form
every time
a
we
set.
cancel two,
So
every time we're actually cancelling two numbers
yeah, you want
and putting
a set.
two numbers.
So main thing
and
about
one
set is that the
when we
order
put
doesn't
one number over here.
doesn't matter.
So it means each.
So
So what that means is what
you can have 1
each
2
number
3.
in this
So
list
one, the set of
is-
1
has actually been duplicated two times. So a
in
set
this
of 1 2
list of
3
24 numbers and a set of
So you can continue
3 2 1 is
doing this
basically the
list.
same
I'm not
set.
going to do.
Yeah, so
I'm
basically
not
you're
going to
choosing
continue,
5
but
numbers,
basically
3
the main
numbers
thing
from
to note is that
here, but the
each
order
number
doesn't
doesn't matter.
duplicate 2 times. So why is that so? So let's say you
so-
isolate the 4-digit
so
number.
let's say
if you're choosing 3
isolate
numbers,
your
and the
1
order didn't
A
matter,
and 1B.
from just now,
So they could be in
the first and last position,
a number
or
of
second,
ways
third position
for this,
But if you
is
just
5
isolate them over 5 minus 3 factorial,
Isolate
over
them,
5 minus 3
then they can
factorial,
either be 1A, 1B,
or
1B,
5
1A.
factorial, 2 factorial, which is
Okay, so
60.
if you isolate them, then there are two
Two or
then
2 factorial ways to
obviously among
arrange
these
them.
16
So that's why you
combination,
see there will
two
be
duplicates here of
a lot
one
of
number
dupli-
here.
a lot of
So let's say you
duplicates of
change it to
subsets,
let's
right?
say,
So
let's find out how many duplicates are there. So let's say you change it to 1 1 1 2.
so you can have
Then you have
yeah,
1A,
so these 16
1B,
ways,
1C.
I'm
So
just going
that
to
means,
roughly list out.
let's say for 4-digit number,
Yeah. Okay, never mind.
to
Isolate. So
the
what I want to
1A,
do is
1B,
I want to do the
1C.
same thing as just now. Where
Then
how
how
many
many
ways are there to arrange
two lists.
One
Let's say you
is
isolate them
where a list.
how many
where
ways
the
are
order
there
matters. So like
arrange
all
it.
of this.
Arrange these three
1,
numbers.
3,
So as you
1,
know, there are
4.
3 factorial
So,
ways, which
one
is
is
also
like
6
this,
ways,
where the order
so
you get
did matter, and one is this, where the
So-
order doesn't matter, but I think the first
yeah,
list will
so
be quite
it's basically
easier. So
if you
in
just
in this such a
So
if you
let's
form a
just
list
start
without the 1A,
so let's
1B,
brute,
1C,
basically brute force a
you
few
get
numbers
and you
here.
expand
1,
it to
2,
this
3,
list. You
1,
get-
2,
each number
4,
here will get
1, 2, 5,
multiplied by 6
3,
times,
4,
so
1, 3,
duplicated
5,
6 times.
1 4 5.
Yeah, so because you get duplicated 6 times, and there are 24 numbers here.
Yeah.
For one,
So
1A,
let's say
1B,
let's
1,
consider one such
1C,
number,
two,
one such set.
you
or
get
whatever. 1 2
4
3
numbers in this list.
So let's say we were
And here,
to
if you
create
continue
expand
for 1 1 2
to
3, you'll get
so 24
over
over
2, which is 12 numbers.
You're
in this
supposed to-
list.
So for 1
Let's
1
say
we are
1,
supposed
2,
to
you get 24 over 6, which is 4 numbers.
expand this set
So
to
basically,
create
in
a-
general, for
let's say you're
that's
you want to
basically your 1.6
associate
lah.
this
So for
number
1.6, if
here
let's
with
say
a few of the
n objects
numbers here,
the
n1
so like
expand
repeated objects
to
and 2 repeated
so
objects,
so on
okay,
until
I'll
n
just
repeated objects.
yeah.
Then
So this
each time
you
your n1 expand to a set of numbers on the
if you
first
treat your n1
list,
objects as
you can get 1 2 3
distinct objects, you
1,
get
3 2 n1 3 n1 factorial
of the duplicate
2 3 1. So you
3
need
1
to
2
divide by n
3
2 1
1 factorial.
So basically you can get 6
get the-
numbers, and that's the same for 1 2 4. You can get 1 2 4 1 4 2, get the correct number. 2
So
1,
basically
4,
basically you do
4,
this for each of the duplicated objects, then this is the number of ways
4
to
1
arrange
2
them.
and 4 2 1. So basically for each number you can, if you you can actually this is called bijection. Biject it to 6 numbers in the first list. Yeah, so basically that means that if I cancel numbers that will create the same set over here, I will cancel 6 numbers here to create 1, 2, 3, 6 numbers to create 1, 2, 4. Basically 6 numbers to create each number here. So since there are 60 numbers here, what I'll get is 60 over 6, which is 10 numbers here, which is indeed the case if you decide to continue listing. So these are the 10 numbers. So why is it that each of these numbers will create 6 numbers over here? So you should note that also 6 is also 3 factorial. So the number of ways to calculate the length of the list over here is also 5 factorial. Can also be considered as 5 factorial over 5 minus 3 factorial times 3 factorial, which is 1 factorial over 2 factorial, 3 factorial, which is 10. Yeah, so this is another formula. So in general, let's say you're choosing R objects from N objects, and the order doesn't matter, then the formula would be N over N minus R, N factorial over N minus R factorial times R factorial. Yeah, so this is the formula. Yeah, so if you generalize this line of reasoning over here, then you can get this formula. Yeah. So now let's say you have 5 numbers, 1, 2, 3, 4, 5. You want to select 3 numbers, but to form a set. So yeah, you want to form a set. So main thing about the set is that the order doesn't matter. So you can have 1, 2, 3. So the set of 1. So a set of 1, 2, 3 and a set of 3, 2, 1 is basically the same set. Yeah, so basically you're choosing 5 numbers, 3 numbers from here, but the order doesn't matter. So let's say if you're choosing 3 numbers and the order did matter, from just now the number of ways for this is 5 over 5 minus 3 factorial, 5 factorial over 5 minus 3 factorial, which is 5 factorial over 2 factorial, which is 60. Yeah, but then obviously among these 60 combinations there will be a lot of duplicates of subsets, right? So let's find out how many duplicates are there. Yeah, so you have, yeah, so these 60 ways, I'm just going to roughly list out. Yeah, okay, never mind. So what I want to do is I want to do the same thing as just now, where I created 2 lists. One is where a list where the order matters, so like all of this 1, 3, 1, 4. Yeah, so one is like this where the order did matter, and one is this where the order doesn't matter, but I think the first list will be quite tedious, so I'll just, so let's list off. So let's basically brute force a few numbers here. 1, 2, 3, 1, 2, 4, 1, 2, 5, 1, 3, 4, 1, 3, 5, 1, 4, 5. Yeah, so yeah. So let's consider one such number, one such set or whatever. 1, 2, 3. So let's say we were to expand to sort by we're supposed to how to say, let's say we are supposed to expand this set to create a let's say you want to associate this number here with a few of the numbers here, so like expand to, so okay, I'll just say so this, when you expand to a set of numbers on the first list, you can get 1 2 3 or 1 3 2 or 2 1 3 or 2 1 2 3 1 or 3 1 2 or 3 2 1. So basically you can get 6 numbers, and that's the same for 1 2 4. You can get 1 2 4 1 4 2 1 2 1 4 2 4 1 4 1 2 and 4 2 1. So basically for each number you can, if you can actually this is called biject it to 6 numbers in the first list. So basically that means that if I cancel numbers that will create the same set over here, I will cancel 6 numbers here to create 1 2 3, 6 numbers to create 1 2 4, basically 6 numbers to create each number here. So since there are 60 numbers here, what I'll get is 60 over 6, which is 10 numbers here, which is indeed the case if you decide to continue listing. So these are the 10 numbers. So why is it that each of these numbers will create 6 numbers over here? So you should note that also 6 is also 3 factorial. So the number of ways to calculate the length of the list over here is also 5 factorial. It can also be considered as 5 factorial over 5 minus 3 factorial times 3 factorial, which is 1 factorial over 2 factorial 3 factorial, which is 10. So this is another formula. So in general, let's say you're choosing R objects from N objects and the order doesn't matter, then the formula would be N over N minus R N factorial over N minus R factorial times R factorial. So this is the formula. So if you generalize this line of reasoning over here, then you can get this formula. Finally, before I go through some tutorial questions, I want to go through how to calculate the number of ways for, let's say, arranging n people around a circular table. So the formula is, for seating n people around a circular table, is n factorial over n, which is also n minus 1 factorial. This is the formula. And for the explanation, I think the tutorial already did it quite. I'm not going to go through because I think the tutorial sort of like did the explanation already, and so and if I were to explain it, it will basically be like creating two lists. It'll be sort of like creating two lists, like what I did just now, and listing out the things on both sides of the list and then comparing. So basically for each rotation, for each arrangement of the table, let's say Like let's say you arrange them in order from 1 in this order, there are always n rotations of this that can appear, that will appear in the n factorial ways to arrange. Or another way you can see it is, let's say the person number 1 to be here at the top of the table. You fix person number 1 to be here, then there'll be n minus 1 factorial ways to arrange the rest of the n people around the table. Yeah. Then in the tutorial, we will also come across like rectangular tables, triangular tables. So just need to know how to rotate it to remove the extra cases. Like here you just divide by 2 since you can rotate it 180 degrees. Then this you divide by 3 since you can rotate it 120 or 240 degrees to obtain the same arrangement. So before I go through some tutorial questions, I think here are 4 rules I think are good to follow when you're solving P&C questions. So first rule is try to link back to what you already learned. So sometimes when you come across a question, it's actually the format is what you learned before. It's just that you have to identify what are the objects and what are the slots you are slotting the objects into something like that. Then number 2 is settle restrictions first. Yeah, so try to settle the restrictions first. Then after you settle the restrictions, maybe you find that you have reduced the question to something you're familiar with already. Then you can just apply the formula and you're done. Rule number 3 is find the complement if it's easier. By complement means I mean like the opposite of what the question is asking you. Like what is, like if the question asks for 1 and 2 ways where arrangements where 1 and 2 are not together, you can try and find the arrangements where 1 and 2 are together. Then you'll find the total number of ways, then you can subtract. Then if that's easier, then it will help you. And number 4 is if all else fails, you can just try, and you have the time, you can try and brute force. And maybe while you're brute forcing, you actually you may actually find a pattern which will actually help you solve the problem. And maybe if the number isn't that big, you may actually be able to brute force all the cases. Yeah. So let's do tutorial question number 1 first. Find the number of arrangements of all 9 letters of the word selection in which the 2 letters E are next to each other. Let's do question A first. So the word is selection, right? So the question says the two letters, there are 9 letters, right? The question says the 2 letters E are supposed to be next to each other. So the way to settle this is basically you treat the 2 letter E's as one block. Then you list out the rest of the letters. So here, even though there are 9 letters, there are only 8 objects over here. So that means you are supposed to slot them into 8 slots. Okay. Yeah. So the number of ways to slot this is 8 factorial from what you already learned before. So the answer is 8 factorial. Then question B says what if the 2 letters E are not next to each other? So to do this, we find the complements, which is rule number 3 of what I said just now. Rule number 3, yeah. So it's basically, instead of finding the number of ways in which the two letters E are not next to each other, we find the number of ways where the letters E are next to each other, which we already found here, and then we find the total number of ways. So the total number of ways to arrange selection is 9 factorial over 2 factorial. Yeah, 9 factorial over 2 factorial. The 2 factorial is because the letters E are repeated. So the answer to B is 9 factorial over 2 factorial minus 8 factorial. Then for question C, asks what if the vowels are not next to each other. So first we identify all the vowels. The vowels are E, I, and O. And the consonants are S, L, C, T, and N. So you're supposed to fit the vowels and consonants into a 9-letter word. Okay, such that the vowels are not next to each other. So so if you don't really know what to do, you follow the rules I said just now. So rule number 1 says try and apply what you learn, but you can't really apply what you learned here yet, right? So rule number 2 says settle all the restrictions first. That means you try and put all the vowels in first, since they are not supposed to be next to each other. Then afterwards you can just put the consonants in and then arrange the vowels among the vowel slots. Then rule number 3 says you can try and find complements, but the complement is quite complicated because you can have, let's say, the complement is not just, let's say, all the 4 letters are together. You can also have, let's say I and O are together, but they are both separate from the letters, 2 letter E's or something like that. So it'll be quite complicated to find. So which leaves us with rule number 4, which is brute force. So let's find the number of ways you can put vowels in the letter slots. So let's start by listing out. You can put in these 4 slots, or I'll just list out the yeah. So these are all the ways. There are 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 14, 12, 13, 14, 15. So there are 15 ways to choose the vowel slots. Okay. Then, yeah, so then within each vowel slot, you are arranging the letters E, I, and O. So you are arranging them in each of the 4 vowel slots. So the number of ways to do this is 4 factorial over 2 factorial, since there are 2 repeated letter e's. Then afterwards you put the 5 consonants in the remaining slots. So the number of ways to do this is 5 factorial, which you already found out just now. You already learned before. So the total number of ways to do this is 15 times 4 factorial over 2 factorial times 5 factorial, which should give you the correct answer. Yeah. Now let's do question number 2. Find the number of 3-letter code words that can be made from the letters of the following words. These are the words. So question A is quite easy. It's quite easy. The word is pairs. The word is pairs, right? Pairs. Then you find that all 5 letters are distinct, so you can just apply formula 5 over 5 minus 3 factorial, which will give you 5 factorial over 2 factorial, which is 60. Yeah. So this is A. Then B, the word they give you is apple. So how do you do this? So by right, what you're supposed to do is supposed to split case based on the number of P's in the word. But let's say you don't know how to do that. Let's say you look at this question, you don't know what to do. So what you do is you can try and brute force. Yeah. So let's say, but when you try and brute force systematically, if not, it's very easy for you to miss out cases. So you may think, after brute forcing for a while, let's just try and brute force. APP, APL, APE. Okay. Yeah. Okay, hold on. Okay, now let's take a look. So let's say we arrange them in order. You can continue brute forcing like PPA, PAP or whatever, but I think if you want to find a system, maybe it's good to find a system now. So let's say you observe APP, you realize we can also form PAP and PPA from it. APL, actually you can just apply formula, which is sort of like you have 3 letters but there are 2 repeated, so the number of ways to arrange is 3 factorial or 2 factorial. Then APL, the number of ways to arrange is 3 factorial. APE is 3 factorial because there are 6 ways to arrange. Then ALE, 3 factorial. PPL, since P is repeated, there are 3. PPE, there are 3 ways. Then PLE, there are 3 factorial ways. So in all you hold on. Yeah, 3 factorial over 3 so is 3. Yeah, so you find there, you add them all up, you get 3,666,336. So there are 4 times 6 plus 3 times 3, which is 33 ways, which is the correct answer, right? Yeah. So by right, the optimal, yeah, so if you want a systematic way to brute force, you can try listing out the number of the letters in the word first before you arrange them. Then you find how to arrange them. So the optimal way to do it is you split into cases based on the number of P's. So let's say there are 0 P's. Then your word will be formed from the letters A, L, and E. A, L, and E. Then you get so the number of ways is 3 factorial, which is 6 ways. Then what if there's 1 P? So there's P something something, right? So there are ALE, you can fit it over here. Choose 2 to fit over here, so the number of ways is 3 over 2 times times 3 factorial, which is 18. Then what if there are 2 P's? So it's PP something, which is PPA, PPL, or PPE. So there are three, choose one ways to select the last letter. Then there are 3 factorial over 2 factorial ways to arrange it. Then you get 9. So you add them all up, you get 33, which will give you the correct answer. Yeah. So the letter for C is raspberry. Actually, in the worst case scenario, if you brute force but cannot find a system, just go all. You can probably just go all out. Like let's say for this question, 33 isn't that big, so if you brute force correctly, then you should be able to find all the possible combinations. So let us see number C, part C is raspberry. So the method to do this question is like just now. You split into cases based on the number of R, since in raspberry the number of R is repeated 3 times. So you split into cases like 0R, 1R, 2R, 3R. Then you just find out for how many ways are there for each one. But for raspberry, if you don't know what to do, you can always brute force and then try and see what to do actually. Yeah, so maybe you can try and brute force a few cases and find pattern, or either that, or let's say the R's, let's say you don't have any repeated letters, then what's the number of ways? So let's say you have 9 distinct letters. So what are the number of ways? It's basically just 9 factorial over 9 minus 3 factorial, which is also 9 times 8 times 7, which is 504. So let's say the 9 letters are distinct, then this is the number of ways. But you know that of course this is not correct, right? So why is this not correct? It's because the R's are repeated. So you cannot. So if you do this way, words like R will get double counted quite a lot of times. So I think from here it's also a motivation to split it into cases based on the number of R's. 0R, 1R, 2R, and 3R's. So you can do the rest on your own. Then the last part is, the last word is banana. Yeah, so by now you probably already realized that the optimal way to do it is split it based on the number of A's. 0A, 1A, 2A, then 3A. But then within each way you count, just make sure you consider the repeated N. Yeah, so for 0A's, your word will consist of the letters B and N. So, and for this there are 3 ways to arrange. 3 factorial for 2 factorial. 1A you can either have BNA or NNA. This will give you 6 ways, this will give you 3 ways. 2A's you can either have BAA or NAA. Both of these to give you 3 ways. Then 3A's you have AAA, which will give you 1 way. So in total this will give you 19 ways, which is correct. Or you can just brute force. So you can have, so you can brute force and see if you can try and see if you can find out the letter, since 19 is not actually that much. So try let's say B A N B N A B N N B A A. Just try and make sure you have a system of brute forcing so you don't miss out cases easily. In the end, and yeah. Okay. Yeah, so these are the 19 ways. Just try and make sure not to miss out any cases. Be careful. If you can, try and find a system. Yeah. Now let's try question 4. Find the number of ways in which the letters of the word elevated can be arranged if there are no restrictions. You can read on your own. So for part I, what if there are no restrictions? Part I considered, so the word is elevated. So the part I, for part I, what if there are no restrictions? It's quite simple, like it's just 8 letters, but 3 of them are repeated, so 8 factorial over 3 factorial equals whatever the number is. Yeah, I should give you the correct answer. Then part 2 is T and D are not next to each other. So one way to do this, so you try and think about how to, rule 2 says you must try and settle this restriction first, right? So how do you settle it? So one way to do it is to sort of like brute force the number of ways you can put T and D in first. So you can put like T, D, T, D, T, D. You can basically list out a number of ways. Then you realize D and T, D can be to the left of T as well. So you list out D, T, D, T, D, T. Then you keep this thing out. Then afterwards you just slot in the remaining 6 letters in the remaining slots to find the answer. But I think the more optimal method would be to rule 3 to try and find the complement. Means you try and find the number of ways in which D and T are next to each other. Then you subtract from the total. So first of all, the total which already found here is 8 factorial over 3 factorial, which is 6720. So now what if T and D are next to each other? So instead of considering 8 letter slots, right, you consider the T and D as one slot, as one block like just now. Then they reduce it to 7 letter slots. Then here are the remaining letters. Yeah, so the number of ways to arrange this is 7 factorial. Is it? Wait, hold on. Okay, yeah. 1, 2, 3, 4, 5. Yeah, 7 letters, 7 factorial over 3 factorial, since there are 3 repeated E's to get 840. Then you subtract from 6720 to get 5880. Is it? Hold on, wait. Oh yeah, wait, hold on. I forgot within the T and D you can also the T and D, the T can be next, it can be either TD or DT. So you need 2 times 2 to get 1680. So the answer is 6720 minus 1680, which is 5040. Yeah. So this is how you do part 2. Part 3 is that consonants and vowels must alternate. So that means that these 4 must be either consonants or vowels, and these 4 must be either consonants or vowels. So you can either have these all consonants and these all vowels, or these all vowels and these all consonants. So within the consonant, so let's say these are all consonants and these are all vowels. So within the consonants are L, V, T, and D. So there are 4 factorial ways to arrange. Then the vowels are E, 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 and A. So for this, there are 4 over 3 factorial ways to arrange, which is also 4. Then let's say these are vowels, these are consonants. That's basically the same. So the answer is 2. That's 4 factorial over 4 factorial over 3 factorial, which is 24. Mm. $192, I think. Yeah, 192. Then the last part is between any two E's. In any 2 E's must be at least 2 letters. So you can't. For this, I think you obviously must try and put the e's in first, right? So for this, I think the best way is to just brute force. So there are 3 e's, right? So you can put it like this. You do a bit of brute forcing like this, or like this. Then you find afterward there's probably no other ways to put the e's, right? So the remaining letters are A, what I mean, A, L, V, T, and D. Then there are five factorial ways to put this in. Yeah, so the answer is 4 ways over here times 5 factorial, which will give you 480. Should be correct. Yeah, 480. Yeah, this is question 4. So let me spend some time to touch a bit on question 5a part 2, which is basically Peter tries to, you have a 4-digit code made up of digits from 1 to 9. The digits may be repeated. So what's the code? How many ways are there to form a code that is an odd number greater than 6,000? So for this, you actually have 2 restrictions. So it must be an odd number and it must be greater than 6,000. So what you note is that for this, let's settle the odd number restriction first. So that means that there are only 5 choices for the last digit, since it can be 1, 3, 5, 7, or 9. Then since the digits can be repeated, right, what you choose for the last digit doesn't influence what you choose for the first digit. So greater than 6,000 means this digit must be 6, 7, 8, or 9. So that's 4 choices here. Then here then the remaining 2 digits, there are 9 choices for each of them. So the number of ways is 4 times 9, 5 times 9 times 9, which is 1620. Correct, right? Yeah, it's 1620. Yeah. For question 6, I'll give you a rough idea of how to do the question. So in a particular, you read the question first. Wow. Yeah, so for 6 part 1, find the number of ways in which the 4 scholarship recipients can be chosen if an order of selection is taken into account. So if order of selection is not taken into account, the number is 7315, right? So what if the order is taken into account? This is sort of like you select the 4 applicants first in no particular order, then afterwards you put them into a certain order. So like first, put them in a certain order, you choose one to be first, then second, then third, then fourth. So for part 1, the answer is just 7315 times 4 factorial. Okay, then find the value of n. So you realize that if the order is essentially not taken, this is basically just n choose 4. So n choose 4 equals 7315. Then for n choose 4, there's a certain formula, right? Yeah, so you basically use the formula and you try and solve for what n is. Then for part 3, actually not really part 3, whatever. So there are 13 scholarship applicants, but 4 of them have to sit together. So for this, you have to settle the restriction first, right? These 4 have to sit together. So for this, you count the number of ways which they sit together first. So it can be here, 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 here. Basically, there are 7 ways which you can place the block of these 4 people. Then afterwards, within each block, you arrange the people, and outside the block, you arrange the remaining 9 people. So now let me talk about question 7. So read the question first. Yeah, so basically you have to 3 single men, 2 single women, and 2 families sit around a round table. Then 2 families have 3 members. So first question says, what if members of the same family are seated together and the 2 single women are separated? So for this, the thing to note is that so there are 3 men, 2 single women, and 2 families. So for this, question, I think it is first of all, since the families are seated together, it's good to, I think you have to treat them as one block. So instead of having 11 block objects, you have 7 objects. Then you treat the family as individuals, as one block. So now you're slotting 7 blocks into a table with 7 seats. 7 slots. So now the question also said that the 2 single women must be separated, right? So for this, so what this means is that rule 2 settle restrictions first, right? So what this means is we put the 2 women in first. So let's say we put the first woman here. Then the second woman must take one of these 4 seats. Okay. So first woman, then second woman, then there's no restrictions for the 5 remaining blocks, right? So it's just 5 factorial ways to arrange them. Then because it's a round table, you are slotting these objects, then you need to divide by 7. Or then in the end you will notice that in each family, the 2 parents and the child, there are 3 factorial ways to arrange them. So it's times 3 factorial times 3 factorial, which should give you 17280 as the final answer. Or alternatively, you can see it like this. Instead of having times 7 times 7, then divide by 7 in the end, you can see it this way. The first woman, because whenever the first woman, you sit her down somewhere, you can always rotate the table such that she is to say in the top position. So wherever the first woman sits down, you fix that to be the top position. Then afterwards, the orientation. So you fix the orientation of the table such that the first woman is here in this particular spot. Then afterwards, you will need to divide by 7 to consider the rotations. So then the woman number 2 will sit here, then 5 factorial, then yeah, that will still give you 17280. Then second part of the question says the seats are numbered and each child sits between their parents. So for numbered seats, let's say for circular table with numbered seats, normally what you do is you find out the number of ways if the seats aren't numbered. Then at the end, you finally multiply by the number of people to get the number of ways with numbered seats. Yeah, so basically you treat numbered seats as non-existent at first. So you treat the seats as they don't have numbers at first. These are numbered. So yeah, so you have so you do it since the families are sitting together, you treat them as one block again, like just now. So again you have 7 slots around the table. Then since the women can sit together now, the number of ways is 7 factorial over 7. Then within each family is parent, child, parent, but the parents can switch positions, so it's times 2 times 2. Then finally, because there are 11 people, you add there are 11 ways to add the numbers for each of them, for each of the seats, so it's times 11. You get, in the end, the final answer is 31680. So I think main thing for circular tables is you need to be careful. You need to know when to divide the number of ways by the number of orientations you can have. Yeah, so here, even though there are 11 people, you divide by 7 since there are 7 slots. Okay, yeah. 8 is kind of hard, and I don't really feel like explaining it, so I'll just skip it. Just remember, for the numbered seats, you multiply it by 12 at the end. Then for number 9, I think the main thing, is just you multiply, you consider all the possible, main thing is you consider all the possible number of delegates from you consider all the possible number of delegates from each of the islands K, L, and M, K, L, and M, and then you just keep multiplying. You just product and then just keep summing up over. Just sum up over all the possibilities. Then for 10 is also the same thing. So let's say, for example, for part A, you have 10 choose 7 first, then there are 3 people remaining, so it's 3 choose 3, 10 times, so it's 10 times 7 times 3 choose 3. Then 3 groups consisting of 4, so here it's basically just 10 times 4, then 6 people remaining, times 6 choose 3, times 3 people remaining, so times 3 choose 2, then 1 person rejected. Then 5 groups consisting of 2 people in each group. It's basically just 10 choose 2 times 8 choose 2 times 6 choose 2 plus times 4 choose 2 times 2 choose 2, but remember to divide by 5 factorial since the groups they can have 5 factorial rate. They are groups, you double counted them 5 factorial times. 11, I think not much to say. 12, 12, I think just follow the rules I outlined just now. Like, first question should be easy. Then it basically, for this, just settle the restrictions first. Like 2 particular canisters, you place the 2 particular canisters first. Then the 2 particular canisters must not be placed next to each other. Then you basically just put these 2 canisters first, find the number of ways you can place these 2 canisters, then you can then the remaining, there are 8 factorial ways to place the rest of the 8 canisters. Should I go? Yeah. So for question 3, I originally wanted to skip this question, but since I cover all the color questions, I think I'll cover this one as well. I think part A should be doable, but for part B, I'll just do part 2 and part 3. point out a few things of part 2 and part 3. So if men and women alternate, so that means so normally for part 2, right, that means men and women alternate. That means you have, what that normally means is yeah, so basically the way to solve this is you place the man first. Let's say to place the man first. Okay, yeah, you place the man first, then afterwards you slot in the women in between the gaps. So there are 6 factorial over 6 ways to place the man, then 6 factorial ways to place the women. So you get whatever answer. You get 86400. So what some of you may do is you may actually place the men and women all together, and then you divide by 12 instead of divided by 6, which is wrong, because like if let's say you're dividing by 12 here, that means there are only 6 ways you can obtain. So let's say one of the orientations is man 1, woman 2, man 2, man 1, woman 1, man 2, woman 2, so on. So the thing is, the way you're counting, right, you can only obtain 6 orientations of this. You cannot obtain, let's say, you rotate until woman 1 is on top here. So you cannot obtain this orientation. You can only obtain, let's say, when the man 2 is here or man 3 is here. So you need to divide by 6 and not 12. Then I think for part 3 as well, I think you put the men in first, and then afterwards you slot the wives in between the men. Yeah, so it's 6 men. Then afterwards there are 2 ways to slot in the wives. So for example, the wives can go to the left of their husbands, or they can go to the right. Yeah, so it's basically just 6 times 2. You're correct. Yeah, it's 240, which is correct. I think that's all for this video. Thank you and bye bye.